Thank you. Yeah, so sorry for the early starting today. I actually changed my slides because yesterday Lei Heng pushed me to talk about Hodge theory and application. So somehow this is now the title appeared on the website. And what I'm going to show is this kind of structure. Basically, what's the Hodge theory? And actually Lei Heng get very basic level elementary introduction about that. So here I would like to point out the linear algebraic version of Hodge theory together with various kind of pictures appeared in literature. And the most focus will be on combinatorial Hodge theory on simplicial complex that will be used for various kind of applications. Well, in particular, I will show some application from computer vision, statistical ranking, and game theory. So that's the basic structure of today's talk. And suppose you might remember in your multivariate calculus course, a theorem like this. This is called Helmholtz decomposition. Means given any vector field on a simply connected domain D, and it can be uniquely decomposed in this form. The first one is called divergence-free flow. Basically, it's a kind of cyclic flow or cyclic vector field. The second is called a gradient field, which basically starting from somewhere and ending with to somewhere. And so this kind looks like a potential gradient. So this decomposition actually happens on the plane with simple connected domain, means there's no holes in the domain. And this picture actually coming from the Gerald Marsden, who passed a few years ago, and Turing's classic book on fluid mechanics. But you probably wonder what's the essence elements in this Hodge theory. So I just give you one particular picture in terms of linear algebra language. So you don't need to worry about anything beyond linear algebra. Suppose you just have three inner product space, x, y, and z, and we have two operator or two matrices, A acting from x to y, B acting from y to z. And this composition satisfies this particular rule. The A followed by B must equals to 0. That's the only constraint we are going to use. And we can define a Laplacian operator like this acting from y to y. Basically, you come from this direction, go A adjoint, because vector in the product space you can always define the adjoint operator. So from A adjoint to A and pull back here in another direction, B and B adjoint, then come back. So this kind of abstract Laplacian operator will be defined in this way. So whenever you have this kind of condition, you can show by linear algebra language the middle inner product space Y always admits this orthogonal decomposition. This is canonical, basically image of A plus kernel of this Laplacian operator and plus image B star. So that's the Hodge decomposition. So various kind of language can be associated with this type of decomposition. You can call homology group or cohomology group depending on what kind of the domain, the field, or the module you are going to use to define the vector space and inner product space. So I won't, yesterday Lei Heng gave you a very comprehensive list of various names can be algebraic topology theory names. But here I just give you the one answer how to prove this simple theorem. So this one turns out to be equivalent to the rank nullity theorem in linear algebra. You don't need to worry about too much. And this to use rank nullity theorem to prove the Hodge theory, basically you can define a big space, take all the x, y, z as a product, and a big operator which consists of A and B in the lower diagonal, and all the other parts equals to 0. And together with this important constraint, B followed by A followed by B must vanishes. And Laplacian we can define a high dimensional Laplacian, make all this stack everything together. We take d plus d star and take square of that. So the d, this operator in physics sometimes we call the Dirac operator, but this is just a very interesting matrix. If you take this d plus d star square, then you get this diagonal matrix. This diagonal matrix, the first part, the first element will be an operator only acting on x, the self-action. And the second part is an operator acting on y. And the third part will be on z. And if you are careful enough, you can see when we develop one-dimensional Hodge Laplacian, this sometimes called a graph Laplacian. This one sometimes called one-dimensional Hodge Laplacian, and this one can be used two-dimensional, but the lower part or down part of Hodge Laplacian. But this you can forget this kind of. Oh, sorry. You can ignore the. Okay, ignore this part for the moment. And these three lines just prove the Hodge decomposition using rank nullity theorem. Consider this matrix. The image of this matrix plus the kernel of its joint must equals to the whole space V. Then if we restrict everything onto the middle Y, what will happen? So in the middle Y, the image of D implied by the image of A. So you take image of A here. And kernel of D transpose, D star, this one appeared here, will be kernel of A star. And this kernel of A star, because we know AB, this composition must equals to 0. So image of A must lies in the kernel of B. Then another direction, kernel of A star must include kernel image of B star. So if you plug in this term, decompose this kernel A star further into two orthogonal subspace. One is the image B star, another is complement, orthogonal complement. Then in the middle, you can replace this condition by the kernel of B star. Basically, the intersection of kernel A star and kernel B, this one gave this quotient space. So somehow from here you can see the previous slide because this kernel must equals to the abstract Laplacian. So in the middle, this Laplacian kernel, so you can put it here. So this is the rank nullity theorem derivation for the Hodge decomposition. So if you are curious what's the linear algebra element behind that, so you can follow this simple scheme. And now this simple linear algebra can carry various kind of structure in terms of different settings. The first version of a Hodge theory coming from a Riemannian manifold. If you studied the Riemann complex, basically you studied the chain map becomes those x and y and z, those in the product space becomes the k differential forms on the manifold, and the operator A and B, those operator becomes the exterior derivative operator, and then you can define this kind of complex we call the Riemann complex, and the Hodge decomposition naturally follows what we described before. And another version is very recent work by Steve Smale and his collaborators. So they study the metric space and Hodge decomposition structure. Now the differential form becomes the square integral functions on metric space X, and you can put finite difference operator, which are often used in numerical analysis and data analysis, and from low order to high order defined in this way. And you can define the adjoint operator. Basically, they are the integral operator. And follow this direction, then you can also find the d squared must equals to 0, and the Hodge decomposition, the algebra naturally carries here. So the third version is what I'm going to use in various kind of application below. Is finite version of a combinatorial Hodge theory. Basically, we study a finite set X, and we build up a simplicial complex, abstract simplicial complex from X. That means we take a subset collection from X, and if any set tau lies in the collection, then all its subset must be also included in the collection. We call this property as closeness under the inclusion or deletion. And when this satisfied, we form a simplicial complex. Then you can define the k-forms as alternating functions, satisfying taking any permutation on the index set. You get a sign, depending on the oddity of the permutation. Then it satisfies this kind of symmetry condition. And the co-boundary map still is the kind of alternating difference operator. Similarly, you can define its joint. And now if we take one particular example, consider a graph. We have an undirected graph, but you can put orientation on the simplex on the edge. And you can blow up the graph into a clique complex, saying you collect all the complete subgraph from G. Then you form a collection. This collection satisfies the closeness and the deletion, the property, then becomes a simplicial complex. Then with k forms, you can define something like that. For 0 form, basically it's a function on the vertex set. For 1 form, it's a skew symmetric functions defined on pairwise vertex. You can on the oriented edges. And 2 forms, basically, our triangular curve is satisfied this kind of alternating symmetry. Then you define the function on the oriented triangles. So co-boundary operator basically just difference operators, and if you take a map from 0 form to 1 form, that forms the finite difference operator on the graph. If you take from 1 form to 2 forms, then basically you take a triangular trace along the orientation of the triangle. Basically, depending on the orientation, you can put plus or minus sign there. We call this kind of operator as curve. And similarly, if you define the inner product, natural Euclidean inner product, or anything associated with this form, you can make a joint operator of them. And the most important property is curl of gradient field must equal to 0. So this you can understand it from very basic multivariate calculus. And one-dimensional combinatorial Laplacian will be defined in the abstract way like this. And in particular, if k equal to 0, that becomes the graph Laplacian. But if you get a k equal to 1, the one-dimensional Hodge Laplacian will be very useful in the later development, like game theory decomposition and ranking decomposition. And these are things the same as before the linear algebra part. The useful things why this kind of structure repeatedly used in from manifold to modern data analysis, because Riemannian manifold and metric space and cell complex, whenever you forget some structure like metric structure, differentiability structure, but everything invariant preserved with this kind of linear algebra, and that reflects some topological invariants like homology reflected in the dimension of kernel of Laplacian. So we don't need those high sophisticated structure, but with cell complex, very natural fitting for data analysis. So we expect this kind of property may make Hodge theory appear in various kind of applications. So the classical application for Hodge decomposition is boundary value problem in PDE. And very recently, there appears a lot of new application from computer vision and to sensor network coverage and statistical ranking and finite game decomposition. So I will pick some of them to illustrate how the idea might be used in various different kind of setting. So in computer vision, very well-known model called the Rudin Osher Fatemi model. They study piecewise constant flow approximation given kind of given an image on the plane for example, on two-dimensional plane. And the piecewise constant flow basically represented by the total variation regularization term. This one basically a L1 norm for if you take this one as a group as a complex number in the plane. In the other language like statistics, they can call it a group lasso. So this one favors a piecewise constant flow. But why we have to use a total variation as to use piecewise constant flow to approximate original image? The intuition is a piecewise constant flow may help you to preserve the edge in the image. However, if the flow, if the original image coming from videos or image sequences, there are often some objects in the videos, and the object may undergo certain movement. So in that case, piecewise constant flow may not be a good regularization to preserve the object, the edges associated with objects. So recently, people suggest use a piecewise harmonic flow to approximate the original one, and this one becomes useful to study the optical flow problem in the video processing. So here it's not quite clear to you, but basically it says there are some object in the receptive field, and the object undergoes some rotation movement. And if you use a piecewise constant flow, then you totally broke the object boundary. But if you use a piecewise harmonic flow, then that's very adaptive to the objects. So illustrate this kind of application. Another application from computer vision. So this example called Adelson's illusion. For example, if you put a column on the chessboard, and the column leave you some shade on the board. So basically, there are two colors, white and black. But under the shading, the absolute intensity inside of the shade will make the white part looks like the black part outside of the shade. So this is the illustrate. So this black part has absolute intensity level at the same level as this white part inside the shade. But although this one happened to be the same of intensity level, for you, you never get confused. This is white, this is not white. This should be black, this is white. You never get confused with these two. How this happened for human eyes? And people suggest that because human eyes only use the... Sorry?
Quick question. So you mentioned the cell complex earlier. So are these, should I think of them as arbitrary cell complexes or as ones embedded in some dimensional? Like are
no,
they
no.
Geometry?
Abstract. Abstract. Yeah, it can be abstract. It can be embedded. Yeah. And for this version, and people suggest to use pairwise contrast to reconstruct the image. That means that we look at the vector field derived from the gradient of the original image, and then use a truncated version to remove the noise, then reconstruct using some sparse reconstruction. So this kind of approach suggested by Osher, sometimes it can be related to Hodge decomposition, but it may not be L2 the version Hodge decomposition. So if you are curious, maybe you can think from this kind of direction. So this second example is from computer vision. The third example actually is from Multimedia Society, a small society within the computer vision. And people wonder, you have lots of videos on the YouTube, for example, or Facebook, you have lots of pictures. And those multimedia content may be the same, but company want to know if we adopt certain data compression technology and how the video content looks good or bad for the reviewers, for the crowd on the internet. So basically, they adopt the crowdsourcing quality of experience experiment, try to evaluate how the technology looks good or bad. So this is kind of another resource for pairwise comparison with a crowdsourcing experiment emerge recently. And this particular example from computer vision called the learning relative attribute, given a pair of given a face from the internet, and you are asked a question, how old this people looks like. It's very difficult for you to give any answer how old. But if you are given a pair of images, then relatively you are easy to tell which one looks older, which one looks younger. So this kind of application, we use a relative, we call it a relative attribute, and age is only one example. And people adopt pairwise comparisons and to collect the data using crowdsourcing platform on the internet. So all these kind of data give you this kind of abstract problem. You are given a graph with a vertex set, those alternatives to be ranked or compared, and the edge set consists of a large number of pairwise comparisons, and different people may vote different pairs, and here some different color. And if you trace back to the classical page rank, that's the one particular version for this kind of data. But more data nowadays rise from multimedia and computer vision and even wine taste psychology study. And this kind of data, how to aggregate into a consistent global preference order or global ranking. This is very classical problem if you can trace back to the social choice theory. So it starts from the 18th century, and people know that at that time majority voting may arise some inconsistency, and especially Arrow's impossibility theorem says that if you follow the majority voting, then all the kind of ranking chaos may happen otherwise, except you take a monopoly structure in the social society rule. But various kind of interpretation for Arrow's impossibility theorem, but in practice people still use statistical majority voting. And the question is how much you can gain from impossibility, how possible you can do that with that. And so here is from statistical society, people can aggregate pairwise comparison using various kind of models depending whether the data is a preference degree or binary choice. You can choose various kind of models, and all these models give you kind of abstract data. You have a pairwise comparison data which are lies on the edge space and which are square integral in the certain sense, and with certain inner product defined by the confidence level. So if you have such kind of data, the Hodge decomposition basically tells you this one. Any kind of data coming from the stochastic majority voting admits such a orthogonal decomposition. And the first component, which is a gradient of certain scaling function on the vertex set. Second component actually satisfies this triangular curl equal to 0. And simultaneously, it has to satisfy the divergence weight equals to 0. We call it curl-free and divergence-free. And these two conditions uniquely decide the orthogonal the projection component here. And in other words, if you put that into a Hodge decomposition, means such kind of data always has this kind of Hodge decomposition. The question is, how can we find these each of the component? The first component actually basically solve the Graph-Laplacian equation and satisfying this one. And the good news is recently people know that for those Graph-Laplacian equation we have nearly linear algorithm, but means there are kind of suggestions from a society like Spielman and Teng and Gary Miller's group. They try to make this kind of algorithm more practical in the practice. But the hard part coming from the second part. So how to compute the harmonic and the curl part. So this is kind of difficult. So what's the meaning of these two parts? For the third part, curl part, actually it accounts for local inconsistency, I call, because on every triangle the total curl should not vanish. But the middle part is kind of tricky because it satisfies both triangular curl-free and divergence-free. Basically, it gives you a circular ranking. We call the harmonic ranking. And this kind of circular ranking generically will pass all the vertex set. So give you a total round order and on those vertex sets. So this one creates all the chaotic voting result once you have any component like this. So this is probably the hardest part in ranking. But the question is how to compute them. And people may think that the curl path seems easier to solve because every Hodge Laplacian has the upper one and the lower one taught by Lei Heng and Cheyenne. And you can solve this upper one solely when you get the projection on the curl part. But the question is the upper part in terms of the Laplacian kind of progress, this curl part equation is not that easy because this one is far away from the being diagonal dominant. In fact, if you look at the Forman's Ricci curvature defined for the Hodge Laplacian, that means if this quantity is non-negative for every edge, then this one Laplacian must be diagonal dominance. This is a kind of equivalence condition for the one Laplacian to be diagonal dominance. So we know if the Laplacian is diagonal dominance, although it's one Laplacian, we can always convert this Laplacian to be some graph Laplacian using some two-color covering, and then you can follow the previous technique for graph Laplacian equation, solve it efficiently. That means that we can find harmonic ranking much more easily in this case. But in general, if it is not diagonal dominance, things might be harder. But the question why the upper part is might be harder to solve than the whole one Laplacian, because if you look at upper part, its Ricci curvature is always smaller than the total the whole one Laplacian part. So that means it tends to be more negative than the diagonal dominance one. So this one is if you pursue the diagonal dominance kind of technique, perhaps this upper part is much harder to solve. So I'm not sure whether this is a good reason to persuade you to move to harmonic ranking computation rather than the curl computation. But there are lots of things inside this kind of question may be considered. And the topological obstructions in Hodge decomposition, because it relies on the connectivity and whether there is a BT1 or loop in the clique complex. So if the clique complex created from the graph is connected, then we can get a global ranking up to a translation constant. And if it is further loop-free, then every harmonic, you don't have any non-trivial harmonic ranking, then you won't have this kind of circular coordinate which creates all the voting chaos. So how to track the topology change? So basically we have using the persistent homology, we can have a polynomial algorithm up to number of cells or simplex in the simplicial complex up to the power 2 point something. It depends on future development, and basically you can use this kind of algorithm to do the it gives an online algorithm for topology tracking if the simplex sequentially enters the stream. And there various kind of problem when in Hodge rank when you try to apply it for cross-sourcing study. And I just list some of them. First important thing is how to design sampling scheme. And so here you can use random graph theory to guide your study. And the second thing is how to deal with the reliability of data. And we can develop outlier detection and robust ranking. And the third one is how to face the streaming data. you need some online algorithm. I won't talk too much about these things, and if you are interested, you can look at those references which appeared in our collaborators and some people in Osher's team recently. So here I would like to give you another application. So this is one of my favorite example of a Hodge decomposition application. So you can use Hodge decomposition to study finite games. In fact, every finite game admits can be decomposed into the Hodge structure that correspond to zero sum and potential game. Very well studied topics in game theory. So if we look how to convert the data, game data into the Hodge decomposition structure, basically you can look at the all the standard form for the normal form of the game. So for example, here is the battle of the sexes game. So you have two person, wife and husband, and each one has two options in the weekend to choose whether they go to see the opera or they go to see the football. And if the husband and the wife both go to the opera, then the wife will be more satisfied, but the husband will be a little bit less satisfied. And on the opposite, if both go to see the football, the husband will be much happier than the wife. And the sad thing is one go to see opera, another go to football, and depending on whether the husband likes the opera or the wife likes the football, the number can vary. But you can put such matrix as the payoff function for each of the player. So the question is, we need to make a graph representing this game. The graph basically consists all the vertex sets as the all the player put their strategy as a vector, then put the vector profile, strategy profile as a node. Then you make up a large graph. Each node represents the strategy profile. And how to put edge between the nodes. So one choice suggested by Pablo Parrillo's group is if only one player changes their strategy, then you use edge, add an edge between them. So that means two strategy profiles are comparable if only if only one user change strategy, because in that particular case you can use that particular user utility as the edge flow. So that maps the data on the graph in this way. So if you take such a data, basically you find you can preserve the Nash and the correlated equilibrium with respect to this kind of data, graph flow data. And suppose you have a joint distribution on the strategy profile space, and which is basically tensor, depend on how many players you have a high order tensor. And if it satisfies this kind of linear inequality, then this tensor must be equilibrium. And in literature, Alban called this one as correlated equilibrium. And if you take a rank 1 tensor, if this one is rank 1, means every player independently choose their strategy satisfying the same set of linear equations, then that's called Nash equilibrium. And both equilibrium actually can be fully decided by the edge flow data when we map the game onto the graph in this way. We don't lose any information about the equilibrium problem. And the question is which equilibrium we should look at. So this is very complicated problem. In game theory, people mostly look at Nash equilibrium. But in reality, Forman suggests correlated equilibrium because they think people never make decisions fully independent in reality. So players decisions may be influenced by its relatives and maybe its close friend, and so decision process may happen in the reality. So he suggests correlated equilibrium may be more suitable to study than this kind of Nash equilibrium fully independent case. But another reason is finding Nash equilibriums notoriously NP-hard. You need to solve polynomial equations, but if you just look at a correlated equilibrium, finding a single correlated equilibrium is a linear programming relatively easy, especially for graphical games. And some natural learning process may converge to correlated equilibrium, but not the Nash equilibrium. So these kind of reasons suggest people to consider correlated equilibrium more than Nash equilibrium. But the question is, can we benefit from this kind of situation to see whether we can find the Nash equilibrium through this kind of structure? Actually, correlated equilibrium contains the convex hull of the Nash equilibrium. It's a non-negative tensor, rank 1 or rank 2 or more rank depending on the number of Nash equilibrium in the set, largely scale in that number. But if a tensor is rank 2, then we know if and only if all its matrix flattenings are ranked at most 2. So that means if you have a tensor at most of rank 2, you can easily just look at all its matrix flattening, use a matrix linear algebra like SVD to find such low rank tensor. However, if you look at the non-negative tensor, if it is as non-negative at rank at most 2, then you need both rank at most matrix flattening rank at most 2 and supermodular. So this situation makes things harder. So can we find low rank non-negative tensor approximation given the linear inequality constraints? This is a kind of interesting question suggested from if we look at the data. If we look at the data from this point of view. And another kind of direction for simplification of games is kind of graphical games. Means we have n player live on a network of n nodes, and every player has utility only depend on its neighbor players. This kind of constraint leave you a joint distribution factorization in the in this product way. It's not rank 1 factorization, but low order interaction depending on the neighborhood size. So you basically can restrict your each factor on the clique, maximal clique, or on the graph. So this one can reduce from the double exponential complexity of representation for this joint distribution to double exponential to maximize neighborhood size. And we hope to have a polynomial algorithm to find correlated equilibrium in some simple graph like trees and chordal graphs. So this kind of structure, and no matter which one before, and we find actually Pablo Parrillo recently suggests every finite game admits a unique decomposition. Means the data when we map to the graph flow always decompose into as a potential game and a harmonic game and a risk neutral game. This risk neutral game means every player can translate their utility by a constant and doesn't change their relative preference, but this one will lead to this neutral games. But the other two will be much more important because potential game and harmonic game both might be easier to solve in literature. So if you consider the sharply Mandela condition in game theory, actually every potential game, every game is a potential game if and only if every triangular curve equals to 0 vanishes. So you can further decompose this potential game by adding quadrangular cells rather than triangular cells. In this case, a harmonic game can be further decomposed into quadrangular curve games. In that way, you can localize the game and make the harmonic part much more localized. And this may give you another kind of way to look at game decomposition. So in particular, if you look at bimatrix game like the example we proposed in the beginning for the battle of sex, such game always decided by potential game by the symmetric part of this bimatrix 1, and the harmonic game is decided by the skew symmetric part. And these parts are very easy to solve because symmetric part, all the pure Nash equilibrium just decided by the local maximum, and the correlated equilibrium will be the convex hull of such a maximum. And a harmonic game actually no pure Nash equilibrium, pure only mixed Nash equilibrium. And what's the benefit if you decompose game into this way? Because if each of them, the potential or zero sum, each of them will be tractable. However, their direct sum is not tractable. It's very NP-hard in the worst case. But if your game is close to a potential game, then you can easily achieve the approximately Nash equilibrium in this case. But on the other hand, we don't know if it is close to harmonic, what's the usage, what's the benefit we can obtain from such a decomposition. So this kind of application for game theory, and so as a summary, I mostly focus on the statistical ranking, and every such pairwise comparison data can be mapped to gradient flow, harmonic flow, and curve flow. And comparably, in game theory, you get a potential game and harmonic game. Why curve doesn't appear? Because you use a clique, a triangle clique, suggested originally by Pablo Perillo. But if you look at quadrangle cells, map them put them into the Simplicial complex, and you get a quadrangle curve flow. So this kind of thing may help you to find the equilibrium, and some settings that you can get tractable. And other application in computer vision, we hope to find more in the future. So hopefully this kind of introduction does not make you feel too much boring with Hodge decomposition. Personally, I like this structure very much, although it's simple, but it appears from very deep algebraic topology to very simple linear algebra. So thank you for your listening, and these are my collaborators and friends. Yeah.
Any questions?
I have a question.
Yeah.
So when you do the, so when you want to get the harmonic free ranking,
Yeah.
when you do that, is it simply a matter of just adding all triangular faces, so you just don't have any holes to start with?
So actually, the original suggestion by Pablo is he only used triangular faces. Actually, he put because every player can change his strategy arbitrarily. Then whenever he change it to a triangle, then he put a triangular face there. But the Shapley-Mandara theorem actually traced the curve along every quadrangle. So you can extend the faces from triangular to quadrangle by adding all the quadrangle. In that case, you can reproduce the Shapley-Mandara theorem and then localize the harmonic decomposition, harmonic game to those quadrangular curve game. So maybe that's useful if the curve is really localized, because typically harmonic game is a global cycle along all the strategy profiles. Okay.
Any questions? Well, thanks again.